Hello everyone. My name is Siddharth Ashokan and I am a PhD student at the Robert Bosch Center for Cyber-Physical Systems at the Indian Institute of Science, Bangalore. My PhD advisor is Professor Chandrasekhar Seelamantola from the Department of Electrical Engineering, also at IISc. Today I will be giving a video presentation on our paper entitled Teaching a GAN What Not to Learn. This paper was presented at NeurIPS 2020. This work is also supported by the Qualcomm Innovation Fellowship 2019. First, let us begin with a brief introduction to generative adversarial networks, or GANs. GANs are a neural network-based generative framework originally envisioned to transform noise to images. Since then, the quality of images generated by these GANs have drastically improved. For example, consider these high-resolution and photorealistic face and cat images generated by StyleGAN. It is near impossible to tell that they're artificial unless one looks closely and knows where to look for the generator artifacts. GANs have found stupendous success in a variety of applications: image super resolution, speech synthesis, style transfer, colorizing black and white images, just to name a few. Now, let's take a look at the generative adversarial network formulation. GANs were originally modeled as an unsupervised training framework tasked with learning a given distribution. Subsequent works have built semi-supervised variants of GANs that can leverage auxiliary information such as class labels, captions, image descriptions, etc. Consider the unsupervised learning problem. The GAN is tasked with learning a target dataset PD, in this case the distribution of celebrity faces. The GAN optimization is a min-max game between two players, the generator G and the discriminator D. The generator network accepts high-dimensional noise as input, usually Gaussian or a Gaussian mixture, and learns to transform it to a target image, which follows an output distribution PG. The discriminator network is a two-class classifier. Its task is to differentiate between the real and generated samples. The game is as follows. The discriminator aims to identify fake images, learning an optimal classifier on the input images it is fed. The generator is constantly trying to outsmart the discriminator, creating samples that are continually harder to classify by the discriminator. The objective is to learn the optimal generator, one that creates samples that are indistinguishable from the reals but ultimately confusing the discriminator. This slide depicts the inspiration for our work. Rumi, a Persian poet and philosopher, said, "The art of knowing is knowing what to ignore." We interpret this in the context of GANs as learning from undesired examples. The premise is that if a generative model learns what it must not fit, it would indirectly learn what it must fit. We achieve this by splitting the data PD into two subsets. A positive class to mimic PD+, which in this example represents the faces of celebrities wearing a hat, and a negative class which we wish to ignore, PD-, which again in this example now represents celebrities without hats. This formulation now gives us a semi-supervised RumiGAN framework. The modifications are lightweight. In comparison to the baseline GAN, the Rumi counterpart merely splits the input data into positive and negative classes, while tuning the loss function to favor learning the positive class distribution. We train the GAN discriminator on both the positive and negative class samples. The optimal discriminator is the one that perfectly classifies its input as positive, negative, or fake. The generator, on the other hand, is influenced by the discriminator to learn the positive class distribution while ignoring the negative class. Intuitively, while the discriminator can be fooled by either positive or negative class samples, the loss function is such that it is easier to confuse the discriminator with positive class samples as opposed to the negative class ones. The result is an optimal generator whose distribution matches perfectly with that of the positive class PD+. Here are some techniques from the state of the art that use somewhat related philosophies. Conditional GANs or CGAN, auxiliary classifier GANs or ACGAN, and their extensions such as the TAC GAN or CGAN PD are class conditional generative models. They are supervised learning frameworks trained with labeled images. The optimal generator learns the distribution of all the classes in the dataset and can generate samples from any class based on the label input given to the generator. On the other hand, complementary learning approaches such as CC-GAN or GAN-POO are discriminative models trained on positive and negative data. These models are tasked with learning an optimal discriminator that can accurately classify new unlabeled samples. In RumiGANs, we take a middle ground approach between these two philosophies. We split the data into positives and negatives, as in the case of complementary learning, but similar to the class conditional GAN approaches, we seek an optimal generator, one that generates samples from the desired positive class. In our paper, we formulate popular GAN flavors such as the Jensen-Shannon divergence-based S-GAN, the least squares GAN, or the Wasserstein GAN within the Rumi framework. In each case, we show that the optimal generator is capable of learning only the positive class distribution. We present illustrative experiments on datasets with balanced positive and negative classes. As an application, we consider learning the minority positive class in an unbalanced dataset and show that RumiGANs outperform both baseline and conditional GAN variants on datasets with simulated imbalances. While we present the results on popular GAN losses, any existing GAN flavor can be brought under this framework. The advantages that the Rumi variants have to offer over the baselines are quite interesting. Consider learning the minority class in an unbalanced dataset of merely 5,000 positive class samples but around 200,000 negative class images. We desire a generator that can generate samples exclusively from the positive class. While a vanilla GAN must be trained only on the desired positive class data, the conditional and Rumi variants can benefit from all the data available, resulting in a more diverse training dataset. This leads to faster convergence of the conditional and Rumi variants. But when it comes to target data generation, the base GANs, which have seen only the positive data, can generate purely desired class images. The conditional GANs can generate data from any class based on the label input. We show that the Rumi GANs can be trained to generate a weighted mixture of these two classes, where we control the weights. This forms a trade-off between the performance of the baseline GANs and that of the conditional variants. Furthermore, the conditional GANs are prone to class mixing. That is, they might generate samples from the wrong class for a given class label. This is more likely to happen when one of the classes has much fewer samples than the others, as in the example considered here. We show that the Rumi GANs can control this mixing ratio through the weights in the loss term. In some cases, such as the Rumi variant of the least squares GAN, we can even achieve perfect separation, generating purely the desired positive class data. This is something the conditional variants cannot guarantee. In essence, Rumi GANs take the best of both worlds, the semi-supervised GANs and the unsupervised GANs. Now, to understand the loss function, we consider an example formulation. Consider the least squares GAN optimization. The discriminator must apply a class label A for the fakes, a class label B for the reals. The generator aims to classify all images to a third class C, thereby promoting confusion. In the Rumi formulation, one splits the data distribution into positives and negative class terms, each with their associated weights, beta plus and beta minus, and corresponding positive and negative class labels, B plus and B minus in this case. The generator continues to assign a class label C to all the images, hoping to confuse the discriminator. We showed that the optimal generator learns a weighted mixture of PD plus and PD minus distributions. Controlling the weights and the class labels, we could learn only PD plus while still training on the negatives. Specifically, setting beta plus as shown, we could make the weight term associated with PD minus, that is the eta minus term, to 0. Since the weights in the loss term, beta plus and beta minus, are still non-zero, the Rumi LS GAN can be trained on both classes of data while learning only the distribution PD plus. Similarly, we derive the Rumi versions of the Jensen-Shannon divergence-based S-GAN. As before, we observe that the optimal generator is a weighted distribution of PD plus and PD minus. Unlike Rumi LS-GAN, the Rumi S-GAN cannot perfectly disentangle the classes. The corner case where we learn only PD plus, or consequently only PD minus, corresponds to training the generator and the entire network purely on the positive data only, as in the base variants. But unlike the base S-GAN or conditional GANs, we now have control on mixing between these two classes. Controlling alpha minus and alpha plus, we can give importance to either learning PD plus or PD minus respectively. The Wasserstein GAN loss can also be reformulated into the Rumi variant by splitting the data term in the WGAN loss into the positive and negative classes. In practice, we enforce the Lipschitz 1 constraint on the discriminator with a gradient penalty term. Now, we will look at a few experimental results. First, consider MNIST. We split the digits into positive and negative classes with some overlapping digits between the two classes. We observe that Rumi LS-GAN learns a more diverse distribution of the desired dataset, unlike the baselines. While the quality of the images generated by LS-GAN is subpar due to the insufficient samples for training, The AC GAN mixes samples between the two classes. RumiGAN has neither of these drawbacks. The convergence of FID or Frechet inception distance scores and precision recall analysis measured with respect to the positive class reinforce these observations. RumiLSGAN converges faster than the baselines, saturates to a more stable value, while generating samples only from the desired class. We also compared the Rumi variants of SGAN, LSGAN, and WGAN on a one versus the rest learning task. The digit phi is defined as the positive class, while all the other digits are the negative class. Yet again, we observe that the Rumi variants outperform their respective baselines. This is due to the increased diversity of samples available for training in all the Rumi variants. As before, the evaluation metrics show that the Rumi SGANs, Rumi LSGAN, and Rumi WGAN achieve lower FID and better precision recall values. Moving beyond MNIST, we present results on unbalanced data as an application. We split the syllabi dataset into female and male classes, sampling only 5% of the female class to represent a positive minority. We observed that the baselines either mode collapsed or mixed up the positive and negative classes. This is observable specifically in the TAG-GAN and CGAN PD cases. On the other hand, Rumi LSGAN learns the target class accurately and is of better quality as compared to the baseline LSGAN. We obtained similar results considering 5% of the horse class in CIFAR 10 as the positive. It's clear to see that the conditional variants, specifically AC-GAN, TAG-GAN, and CGAN PD, invariably learn the wrong class distribution, generating images that look nothing like horses. While LSGAN mode collapses, Rumi LSGAN does not. The evaluation metrics clearly indicate the superior performance of Rumi LSGAN in both the CELEB and CIFAR 10 cases. We obtained similar results on high-resolution CELEB, simulating a minority on the female or male classes as before. We also trained on truly imbalanced classes of CELEB, such as the hat or bald classes, having 5,000 positive images in comparison to around 200,000 negative images. Rumi LSGAN generates a diverse set of high-quality images, all from the desired positive class. In conclusion, we present the novel Rumi formulation to train GANs. Any GAN variant can be trained with negative samples while learning only the distribution of the desired positive class. We presented the Rumi counterparts of various standard GAN flavors present in literature and demonstrated the ability of Rumi LSGAN to outperform classifier-based models on both balanced and severely unbalanced datasets. While we simulated imbalances as a proof of concept, in practice, the choice of positive or negative classes is a problem-dependent one. Real-world applications with inherently imbalanced data will benefit greatly from the Rumi formulation. For additional insights, proofs, and experimental results, please check out our paper. The source code is also available at our GitHub repository, which can be accessed by scanning the QR code here. Thank you all for your attention.